Assalamualaikum. So we're going to continue our discussion on Grover's algo. And I ended the previous lecture with a question, but before I re-inquire of that question, let me draw the circuit again as it is currently evolving. So our particular example was focused on a 2-bit string, and we're looking for a certain combination in this 2-bit string. We add a third ancillary qubit, initialize our quantum computer such that all the 3 qubits, the 2 working qubits and the 1 ancillary qubit, is in the state ket 0. Apply a Hadamard on the working qubits, invert the ancillary qubit and apply a Hadamard. So at this stage, we do know that we will have a specific quantum state, and that quantum state will be given as ket 0 plus ket 1 over under root 2 for the first qubit, ket 0 plus ket 1 over under root 2 for the second qubit, and the ancillary qubit will be ket 0 minus ket 1 over under root 2. So if you look at the first 2 qubits, it's in an equal superposition of all the 4 basis states for the 2 working qubits. In other words, you could write these 2 working qubits in this form. Right? Alright, and the particular string that we're searching for in this example, because we have to build an oracle, is 1, 1. So this state somehow interests us, this one. And we would like to build a quantum oracle that can pick out or sample this state from the others. So knowing that this is our search string, this is the solution of the algorithm. We design an oracle which gives as an output on one particular qubit. If that one particular qubit gives a flash or it is in a certain state, one could tell that the working qubits are in the state ket 1, 1. And the particular kind of circuit that we designed was a Toffoli gate. And this design will change if our search string that we're looking for is different. So knowing that we are looking for this particular string, we design an oracle, and we say that this oracle implements a unitary operation. Every operation implements some kind of unitary gate, and we already learned that what this gate does is that it creates a new state, of course. And if we focus our attention on to this particular subspace, just this subspace, and forget about the ancillary qubit, because everything is separable, we learned from our previous lecture that out of these 4 component states, the phase of this state is inverted. Correct? Because of the particular design of this oracle. The oracle says that if the first 2 qubits are in the state 1, 1, then this qubit is inverted. When this qubit is inverted, a phase of -1 is picked up by this state here. It gets kicked into the first 2 qubits. This effect you've already seen in the Deutsch algorithm as well. The phase that appears in the ancillary qubit gets kicked to the working qubits. This is called a phase kick up. So in this particular regime, in this subspace, the new state that has come out as a result of the application of this oracle is this state. I'll be to the negative sign here. So if I were to write this state in a different kind of box here, now I have a 2 qubit state because I forget about the ancillary qubit. I'm not going to do any measurement on the ancillary qubit from this point onwards. My quantum state will be of this form: 0, 0, plus 0, 1, minus plus 1, 0, minus get 1, 1. If my search solution was some other string, say 0, 1, this state would have picked up a 0, a minus sign, and I would have designed my oracle so that this would happen. Now where do we go from here? From here we apply another sequence of gates. We don't know how to build those gates, but we do apply an operator. And the operator that we apply is, so we're going to see how do we implement this operator, but we already know that we have a special kind of operator here, and this was Grover's insight, and that operator has a form. So we don't care about the ancillary qubit. I don't know why I'm drawing this over and over again. So the ancillary qubit just goes where it is. My subsequent operator here takes this form: 2 ket psi graph psi minus identity, where psi is an equal superposition of all the 4 basis states, computational basis states on these 2 qubits, which means that psi is 1 half 0, 0 plus 0, 1 plus 1, 0 minus plus 1, 1. Got it? So now the next question is, how do we implement this gate? So we'll come to that in a minute. But first of all, let's see what is this gate really doing. This gate has a special impact on an input state. The input to this box is this particular state. So let's call this psi 1. So this state here is psi 1, right? This is psi 1. And let's apply this operator on to this input state. Let's for the time being call this operator A for amplification, or a better symbol would be, say, F. Okay? So if F acts on psi 1, which means that 2 times ket psi graph psi minus identity acts on psi 1, which is 1 half 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. This phase has been kicked out from the previous application of the group of the oracle, the quantum oracle. We already discussed what's going to happen to this output, the new state that is going to be produced as a result of the application of this operator. So what it does is that it takes each of these amplitudes and subtracts that amplitude from twice of the average of all of these amplitudes. So the output would be, so what's the average of these 4 amplitudes? Half, 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 minus half. The average is 1. 2 times 1 is 2. So 2 minus half is 3 by 2. 2 minus half is again 3 by 2. 2 minus half is again 3 by 2. And 2 minus half is 5 by 2, right? Plus 5 by 2. Got it? So remember that we learned from our previous lecture that 2 times get psi, graph psi minus identity on some arbitrary state, AI, get AI. This is some arbitrary quantum state. And this get psi is an equal superposition of all the basis states, right? Remember that. We already learned from our previous lecture that this outcome is, everything is expressible, of course, in the same basis state, but the amplitudes change. And the amplitudes change such that each AI is converted to 2 times the average amplitude minus that amplitude. Right? So this was from our previous lecture. I've just applied the same formula over here. Now if I look at this particular state, let's call this psi 2. This is the state that is produced over here, psi 2. Yes? Sorry? We're just ignoring that third qubit. There is a third qubit, but so there is an identity operator on the third qubit. Right? So we do not have anything to do with the third qubit from this point onward. We're just ignoring it. Ignoring it means we're just applying the identity operator to the third qubit. Is that okay? Why? Yeah? No, why? Because this is a 2 qubit state. This psi is a 2 qubit state. So 3 qubits are coming out from this oracle. 2 working qubits and 1 ancillary qubit. Now we do nothing to the third qubit. And you're applying some logic gate, some unitary operation to the first 2 qubits. Not concerned with the third qubit. And at this point, there is no entanglement between the first and the third, or the second and the third. They are all independent. So this part is separable from this part. Yes? करेगा, लेकिन this is something we learned from our previous lecture. So here an equal superposition is created for the first 2 qubits with the third qubit, albeit with the minus sign here. So when this Toffoli gate is applicable, this combination is going to change the sign of the overall sign of this amplitude, and that phase is picked up by it becomes a relative phase over here. Just do it on your notebook. We did it in the previous lecture as well. क्योंकि हम ना करो इग्नोर, साथ लिखते रहो, ना करो इग्नोर, जो भी उसकी आउटपुट है लिखते रहो, आपको कोई नहीं रोकेगा, लिखते रहो, लिखते रहो। हाँ, फिर इस पे आपको एक एंसर्ड आइडेंटिटी भी करना पड़ेगा, लिखते रहो, ना करो इग्नोर। If nothing is happening to it, so it's as good as nothing. The identity operation acting on something doesn't change that thing, right? And all measurements are done on the first 2 qubits anyway. Yes? वो एवरेज था, वो ये था। अच्छा ये था ना, तो यहाँ पे n क्या है? 4. Right. So this is all right. So this is, each amplitude is 1/2. So this just goes away. So we have 1/2 plus 1/2, which is 4, which is 1 divided by 4. So it becomes 1/4, right? All right. So okay. So you have to multiply this with 2 as well. It becomes 1/2. All right. So thank you. 1/2. 1/2.
You also have to subtract. Also to subtract the AI.
Yes, 1/2 minus 1/2.
0.
Only the last one survives.
In this particular case, only the last one survives. Okay. So our AIs are 1/2, 1/2, 1/2, 1/2, and minus 1/2. The average A is the sum of these, which is 1 divided by 4. So I multiply this with 2, so I get 2 times A minus AI. This is 1/2 minus 1/2, 0, 0, 0, and 1. Correct? Alright, so well and good. So all of this just disappears. Thank you for this. I'm just left with cat 1, 1. And this is happening here because we just have a 2-qubit state. For higher dimensions, this might we'll have to do some additional iterations. Anyway, so at this stage, in psi 2, we just left with cat 1 here, cat 1 here. And if you were to do a measurement here, so we could have a beam splitter and do our conventional measurements in the 0-1 basis. Each time, cat 1 is going to give a click here and detector number 1 is going to click here. So you will always be able to tell that this is the solution. So this is how this algorithm is working. And if all of this, by the way, all of this is called a Grover iterator. G. Grover iterator or a Grover diffusion operator. What the Grover diffusion operator is that it implements the oracle OF followed by this operator 2 cat psi graph psi minus identity. So what is this operator really doing? What is conceptually the role of this operator? It amplifies the desired state. So luckily in this case, since we're dealing with 2 qubits, by the way, this only happens for 2 qubits and all the other states just vanish away in one iteration. This is just a lucky kind of example. All other states are diminished and the state that we're looking for is amplified. Right? By the way, these are probability amplitudes. So if you want to find out the probability, you have to take the modulus square. So in this case, the probability of detecting 0, 0 on the first 2 qubits turns out to be 1. So 100% certainty. Right? Because this is the only state that survives. Got it? So the question is, how do we know which state survives? So the calculation is in front of you. What happens is, at this particular, so we create a superposition here. And the superposition is special. The state that we're looking for is somewhere in here. Now this third qubit is in this particular state, and there's a minus sign here. Alright. So this minus sign is really important. Let me just finish one thing, right? So here a superposition is created with the help of these Hadamard gates. If this NOT gate didn't exist, an equal superposition would have been created, the plus sign here. But this NOT gate has injected a negative sign into our calculation. So what we hope is that we're going to exploit this negative sign here. So we've designed an oracle. The oracle does the following. The state that we're looking for, if both of those qubits comply with the state that we're looking for, that is, if this is in state 1, this is in state 1, that's the state that we're looking for, that's the string that we're interested in searching for, conditional upon achieving this combination, we invert this qubit. And when we invert this qubit, a negative sign appears here. Alright, and if we were to write out the state, expand out the 3 qubit state, eventually a negative sign will appear over here. Now we have created from an equal superposition, so now just focusing by the way on the first 2 qubits. And from an equal superposition, we started off with this, on the first 2 qubits, somehow we've inverted the amplitude corresponding to the state that we're looking for. That's what this oracle is doing. So we have designed it in a way that the phase of the search solution is inverted. Now we have to come up with a subsequent algorithm or a circuit that takes up the state that is distinct from every other state and amplify it. If you were just to measure the probabilities associated with these 4 states without this subsequent operator, each probability would still be the same. 25%, 25%, 25%, 25% here, because there's 1 half, 1 half, 1 half, 1 half. And this phase wouldn't really matter, right? Because the probability amplitude squared just washes away the negative sign. So what you would now like to do is you would like to make these probabilities different in their magnitudes. Here the 4 probabilities, this might have different sign, but the 4 probabilities are the same magnitude. So now you would like to make the probability of that term different from the others. So how would you do that? You do that by this particular algorithm, this particular circuit. And what this does is that it subtracts each amplitude from twice the average of the amplitudes. And when we do that, it happens in this 2 qubit case that all other amplitudes just vanish and this one survives. This goes away, goes away, goes away. This particular term survives. So we've done amplification at its best. This is like a notch filter. It just washes away everything and keeps one particular term intact. And now you were to do a measurement, which means you have beam splitters at the end which could distinguish, tell whether each qubit is in cat 0 or cat 1. Only the cat 1 channel is going to light up all of the times whenever you repeat the experiment with the same input states. And everything is repeated in an identical fashion. So you would tell that the first 2 qubits are always in the state 1, 1, and that's the string that you're looking for. So this is how this algorithm is really working. Now there are 2 or 3 questions that remain. By the way, in this example, the probability of getting 0 on the first qubit and 0 on the second qubit is 0%, sorry. This is the same as P01, P10, whereas the probability of getting 1 and 1 on each of the first 2 qubits is 100%. So our algorithm works perfectly in one shot, in one go. in this example. So even though classically, if you would like to find out one string from 4 possible strings, the worst case scenario is that you would like to have, may have to make 3 queries. 3 queries because it's possible that in the first 3 queries you wouldn't find your search string. It might be the 4th one. So if it doesn't appear in the first 3 queries, it has to be in the fourth location. So now we've just done this measurement in one shot. Now there are 2 questions that remain. The first question that remains is, how do we implement right? This is one question. So what kind of circuit do we need to build? The second question I would say is, if the number of qubits is larger, can I still find the solution in one go? So how many iterations are needed? So another form of asking this question is, what is the complexity of this algorithm? How many times do I need to run this algorithm? So this lands me to the question of complexity. So we'd like to answer these questions. And the third thing is, which is related to the first point, is there a geometrical interpretation of all of this? By the way, what if our X star, the solution or the string that we're looking for, is not one string, it's say 2 strings? What if my search solution comprises 1, 1 as well as 1, 0? Then what's going to happen? Yes, question please.
Sir, why is it called Grover diffusion?
It's called Grover diffusion because if you look at the, I'm going to describe a geometrical interpretation. There's a vector in a space that is moving, it's diffusing. That's why it's called a diffusion operator.
सर
Yes.
जब वर्टिकल आइटरेशन या इंक्रीज होती है तो हम शुरू से दोबारा स्टेप उसी स्टेप को देखते हैं?
नहीं. So let's look at the entire scheme of this algorithm. So I initialize my quantum circuit in this fashion, right? So this is a big bold 0, so this could be n qubit big. This could be n qubits. I initialize all of them in the state 0, 0. So this is just shorthand for writing 0 n times. My third qubit after the initial NOT gate and the Hadamard gate is in the superposition. Then to this I apply my oracle, and the task of the oracle, as we learned in the previous class, is that it takes a ket X ancillary qubit in a state Q. This is a single qubit and does nothing to X but creates an exclusive OR of Q with the function that we're looking for on X. And we've defined our function such that f acting on x is 0 if this x is not the same as the solution that we're looking for, and it's 1 if this x is the same as the solution. This is how we define our f. So we apply an oracle, and what this oracle does is that the solution that we're looking for gets a negative sign. So a negative phase appears on the solution. This thing. And then we apply an operator which is 2 times ket psi bra psi minus identity. What this does, it amplifies the amplitude, the probability amplitude that comes with x star. So the algorithm overall does the following. It applies OF on the initial, so let's call this an initial state. This is my initial state. OF tensored with identity on the ancillary qubit, followed by 2 ket psi bra psi minus identity tensored with identity on the ancillary qubit. So I'm doing nothing to the ancillary qubit. So I explicitly write the ancillary qubit here, the third qubit here, because I've written it in my initial state as well. Right? So all of this, when I do multiple iterations, it's basically applying this operator. All of this is called the Grover operator. I apply this operator multiple times. That's what doing iterations means. So I apply this operator, say, k times. That's what the iteration really means. So I don't have to restart putting in more initial states and repeating the experiment right from scratch. I just apply this Grover operator G k times, right? And I would like to tell how many iterations are really needed so that I zero in onto the solution that I'm looking for. And do I ever get to the solution? In the case of 2 working qubits, I do get to the solution bang in just 1 iteration. But this is pure luck because we just have 2 qubits here. Alright, so now before we start looking for implementations, so we need a quantum circuit. So if you want to build this on a quantum hardware, or you would like to run this on a quantum simulator, and some homework problems I think will revolve around implementing this on a simulator, on a real or on a real computer, you have to build it in hardware. So what kind of gates do we need to build this operator on a hardware machine? Yes, please.
सेकंड आइटरेशन के लिए इनिशियल स्टेट क्या होगी?
So the output of this thing will be the initial. So it's not an initial state; it's a repetition of G. What do you mean by you do? That's so the next iteration of G will use the output from the first iteration. So this is what's going to happen. So you have an initial state. You apply Gk, G, and then you apply G again, right? And you apply this k times. Just look at the final, these 2 qubits at the end, right? Right? So you apply this k times. And you zero down on or track the solution. So I'm going to show that how that is done if we were to look at the geometrical interpretation. So let's move on to the geometrical interpretation, right? G.
सर जब एक दफ़ा ये ग्लोबल ऑपरेटर अप्लाई होगा तो हमारा इनिशियल स्टेट तो फिर ट्रांसफॉर्म होके फाइनल कोई नया स्टेट बन गया तो फिर उस जो एंड पे हमारे पास एक फाइनल स्टेट बन रहा है जो इस केस में कैट 1 था तो ग्लोबल ऑपरेटर उसके ऊपर अप्लाई होगा
नहीं, if you just have 2 qubits, then your final state is the solution that you're looking for in one shot. You just need one application of the Grover operator.
अगर मल्टीपल क्यूबिट्स नहीं है
So if you have, instead of 2 qubits here, you have 3 or 4 or 5 or 6 or 100 qubits, then you would need multiple iterations to zero down onto your solution.
अगर मल्टीपल क्यूबिट के केस में एक दफा जब ग्लोबल ऑपरेटर लगेगा तो द आउटपुट विल बी डिफरेंट देन द इनपुट जो हमने स्टार्टिंग में फीड किया था.
You don't want, you're not trying to track what the input is. You're trying to create an input and find your solution from the inputs. You're finding a needle in a haystack. You have a very large pile of things. There's one pearl hidden in that pile of rubbish, and you just want to find that pearl from it. That's what the Grover algorithm is doing. It's just zeroing down onto the solution and removing all the shaft. It's separating the shaft from the wheat.
ठीक है. और जो बीम स्प्लिटर है वो हर ग्लोबल ऑपरेटर के बाद अप्लाई होगा.
I mean, the beam splitter is just a conceptual representation of a measurement. You want to project onto cat 0 and cat 1. That's showing the measurement scheme.
और वो k times apply.
So after you're done with all the k iterations of G, at the end you want to measure. That's it. Yes, please.
Is the initial state always going to be a state which will come from EH or NH to get उनके बाद? Is it always going to be that?
So in most quantum algorithms, it's easier in hardware implementations to create this state than a superposition. So you create these states. These could be ground states. If you look at an energy manifold, and so everything has a certain Hamiltonian. You want the system to start off in the ground state of the Hamiltonian. Let's call that state cat 0, 0. So it's easier to start off in this computational basis. And then, however, quantum computer is only useful if you create a superposition. So these Hadamard gates create a superposition. So does this Hadamard gate. The only point why we have this NOT gate at the very beginning is that you would like to tickle in that negative sign into the quantum state. So that negative sign then gets kicked up into the amplitudes of the solution that we're looking for, which is hidden in a heap of other unwanted things. Okay?
So in general, if we have 4, 5, 10 qubits,
Yeah, so
the last qubit will have NH, right?
right, so you have, say, you start off with n qubits. You can write this in many different forms, right? And then what you would like to do is you would like to do a Hadamard gate times a Hadamard gate, n times, right? N times. Okay, so a big Hadamard gate. That's what you would like to do. By the way, sometimes if I were to use n qubits, the number of states is, the possible states is 2 raised to the power n, by the way. Sometimes, really I should distinguish between small n and capital N, but do excuse me if I just, in interest of time or just being sloppy, I just miss out. But generally I talk about small n qubits and capital N states. So here my small n is 2 and there are 4, it's a 4-dimensional Hilbert space for those 2 qubits. So now let's look at a geometrical interpretation, and that will cast another light and another perspective on this algorithm. By the way, this algorithm, the Grover iteration algorithm, is a search algorithm. It has a merit of its own. It has a standalone quality as well. If you want to search from a database or from another collection of objects and you want to search a particular string from it, so it has its standalone merit, but this also becomes a routine or a subroutine, as you call it in computer science or programming, for other algorithms. Okay? Alright, so let's look at a geometrical interpretation. And how do we do that? Just a second. Alright, so suppose I draw a circle. And this is not not a block sphere because I'm not talking about one qubit now. This is a higher dimensional Hilbert space. But for purposes of geometrical interpretation, I'm just drawing a circle. And there's a particular search vector that I'm looking for. Suppose that search vector is ket x. This is my solution. Alright? There are, so this is one of the basis states that I'm looking for. For example, one of the basis states, my search was looking for ket 1, 1. That's my ket x. But there are 3 other basis states as well. So let me define a vector y which comprises of all the bad states, that I'm not looking for. Alright? So this ket y is a superposition of, say, an equal superposition of all the ai's 1 over, so there will be n minus 1 of those ai's. So these are all the ai's for which is 0. So I create an equal superposition of all the states that I'm not looking for. So for example, in this 2 qubit case, this would be my ket y. Alright, so conceptually, this ket x lies somewhere on the circle, and there is also a ket y that lies somewhere else. And really, this state is orthogonal to this state. So orthogonality is not like, I'm just conceptually representing that orthogonality to represent a 90 degrees angle, but there's no real 90 degrees angle. This is just a conceptual diagram. Alright. Now let's see what is the role of this operator and what is the role of this operator. Alright. Just give me a second. Alright, so when I'm at this location, at ket here, let's call this state over here ket psi naught. Now what is this state ket psi naught? Ket psi naught is an equal superposition of all of the 4 basis states, of all the n states, capital N states. Alright, so ket psi naught is the state that I'm looking for. Say, let's call it x. So x star is now just x. 1 over under root n plus everything else, which is ket y, but I also need to normalize this property, so I put n minus 1 over n here. This keeps everything normalized. So this is my state psi naught that is being fed into the Grover, into this operator, into the oracle, quantum oracle. This is my solution x, what I'm looking for. I represent this on this diagram by this point, this location. This is my unwanted, my undesired solution. This is the dross from which I would like to separate out these pearls. Okay? Now, this ket y has been normalized over here. So I am being careful about normalization. That's why I put 1 over under root 3. Or for n qubits, small n qubits, this will be 1 over 2 raised to power n, or 1 over capital N, this thing. So there will be 1 over n minus 1, sorry, because there is one solution. There are n states. One of them is a solution, so there will be n minus 1 unwanted states. So this factor is n minus 1. And when I combine the two so that my overall state remains normalized, I need to put a 1 over under root n here and a 1 over under root n here, but in the numerator I put a square root n minus 1 so that this cancels off this, so all of this remains normalized. Got it? So every state that I am writing is normalized. Yes, please.
हाँ वो y में under root 3 और 4 नहीं होना चाहिए.
If you take the modulus square, 1 over 3 plus 1 over 3 plus 1 over 3 is 1. This state on its own is normalized.
नीचे हमने formula लिखा है n minus 1 over n.
So this will be 3. This will be 4, but this square root of 3 will cancel out this square 1 over under root 3. So I'll be left with 1 over under root 4, which is 1 half here. Okay? So now this is the state that is being fed into the quantum oracle. Correct? It's an equal superposition of all states. The wanted states and the unwanted states. That's what you're feeding into the oracle, right? So this is what is being fed in over here. Wanted and unwanted, everything with equal propensities coming into the oracle. And somehow the oracle's task is to create a nudge on the wanted state. Now where does this state lie on this circuit? Somewhere here, right, in this quadrant. Is it closer to this or closer to this? Same? Why? So this is 1 over 4, 1 half. This is 3 over 4. Right? Square root 3 over 4. So under root 3 over 2. So I think this will be 60 degrees, this will be 30 degrees. So this is where the state psi naught lies on this geometrical interpretation. Alright? Now, this is what is being fed in here. Now what does this operator do? What does this operator do? It changes the sign of the wanted state. But nothing happens to the unwanted parts. So what the first quantum oracle would do is that really it would like to take this state and bring it here. So what, because this state has the same direction cosine with this orientation, the unwanted part remains the same, but the sign of the wanted part is inverted. So this is the action of the quantum oracle. That's what appears here, right? So this is ket psi 1. So we've looked at what this algorithm is doing up till this point, up till after the quantum oracle. Now let's see what this operator does to this kind of geometric picture. Right? So we know what this does. Let's see what does this do. Any ideas? Right, sorry? So this is just an orientation. The state lies on this orientation. Amplification doesn't really mean that you increase this thing. Yes? Counterclockwise or clockwise? So you want your final state to lie close to this state. Right? So the idea, the intuitive idea, the commonsensical idea is that the two ket psi, drop psi, minus identity operator should really try to bring this state psi 1 back into a new position psi 2, which is as close as possible to this orientation, right? Remember, this is 60 degrees. So this is 60 degrees, this is 30, this is 30, so this would also be 60 degrees. So keep these angles at the back of your mind. And this angle therefore is also 60 degrees. So what these two, alright, so let's see, suppose I have some state, just an arbitrary state psi, right? Okay, and another quantum state, say, let's call it chi. All right. So I would like to find out the action of 2 times ket psi, bra psi minus identity on chi, geometrically, right? I know that if this were the equal superposition of all states, what this would do to this particular state, if I knew the probability amplitude. But let's look at this from a geometrical perspective. How do I do that? I know that if I have a state psi, there is going to be another state psi perpendicular, so that the overlap of psi with psi perpendicular is 0. So these two states are orthogonal to one another. I know that that is always going to be the case. Such a state will always exist. So this means that the state chi can be written in the basis that is spanned by chi and chi perpendicular. Chi and chi perpendicular are two vectors orthogonal to one another, and they span the entire basis. Why do they span the entire basis? Because in this geometrical representation, if this is ket x, then this is all the rest, ket y is all the rest of the basis states. So these two vectors will span the entire basis. So any two vectors, any vector that we draw on this picture has to be written in a particular basis. And if I write two vectors, then those vectors in such a fashion that they are perpendicular to one another, then the two orthogonal vectors which are linearly independent will form a basis. So any vector chi can be represented in terms of the basis that is spanned by psi and psi perpendicular. If this is one vector, one basis vector, this is all the rest. And all the rest which are perpendicular to this. Right? So every vector can be written down in a particular basis. And the basis by definition spans the entire Hilbert space. So this chi could be represented by alpha, a component alpha in the direction of psi, plus some component beta in the direction of psi perpendicular. Got it? So now what we would like to do, what happens if this operator acts on chi? Let's see. So 2 ket psi bra psi minus identity acts on chi, which means 2 ket psi bra psi minus identity acts on alpha chi plus beta chi perpendicular. So this means, now let's have this operator act over here. This gives me 2 alpha chi. When this operator acts on this state, this inner product will give me 0. So forget about it. Now this operator has to act here. So I get minus alpha chi minus beta chi perpendicular. So this gives me alpha chi minus beta chi perpendicular. So when this kind of strange operator, let's call this the amplification operator, acts on some arbitrary input state, then what is it going to do? So by looking at this solution, can you identify what will it do geometrically to the state chi? So alpha, by the way, is just the probability amplitude. This thing is the probability amplitude of this state on to this. So it's the inner product of chi with psi. And beta is the inner product of chi with psi perpendicular. Exactly. It's going to be a rotation, not a reflection. It's going to be a rotation about this axis. A rotation about this axis, right? In this fashion. So this is going to rotate. So if this angle were, say, gamma, then after the application of this amplification operator, the new state will appear on the other side of chi such that the angles are preserved. So it's a 2 gamma rotation towards chi. So it's a reflection operator. So this amplification operator is really a reflection or a rotation operator. Okay. So let's use this same argument over here. Yes, please.
Only the sign of beta is changing.
Mm-hmm. So when you have vectors, what is this being reflected against? So is this the reflection plane? So what you would like to do is you would like to pick this vector and rotate it on this circuit. And the amount of rotation is you get back here, the angle that you've spent on getting to this axis, you move further by the same angle. So what is happening here is that this sign isn't changing. So the projection or the cosine of the angle is not changing with this psi, which means that this vector and this vector have the same projection on this line, on this vector. However, this thing is changing, so the projection along this, parallel to this, is changing its sign. That's what's happening. So this reflection or this rotation operator is reflecting or rotating about this particular axis, which is formed by this state. So now if you look here, what this amplification operator is going to do, what is it going to do? It's going to rotate about this state. So it's going to bring this state back here. So it moves by 60 degrees and moves another 60 degrees and comes back bingo in parallel with our solution. Alright? So this is a geometrical interposition. What if you have a more complicated scenario? What if you didn't have these 2 qubits, you had more qubits? Then things would get slightly more complicated. Alright, so you wouldn't be able to get back to your desired solution in one go. You will have to do multiple iterations. And that can tell you how many iterations that would you really need. So let's do that for a minute. All right. So suppose this is the geometrical pattern that I'm looking for. This is my state ket x, my solution. This is my ket y, and my so this is the state that I start off with, an equal superposition. Let's, what have I called this? Psi naught. What is this angle? The cosine of this angle is, so I take this state, find a projection along ket x, this will be 1 over under root n. So this angle here, let's call it gamma, is cosine inverse 1 over under root n. Right? This angle will be the cosine inverse of this thing. Okay. Next steps. So this angle is really, this thing is cosine inverse n minus 1 over n under root. Okay, this angle. So I do know that the oracle is going to invert this state about the y-axis, right? Because it's just going to change the sign of the component of psi naught that is along ket x. So I will, this is what's going to happen after the oracle, after OF. And this angle is the same as this angle. Right? So overall, the angle here, this angle is 2 times cosine of n minus 1 over n under root. Now this is an equal superposition of all the states. So this is the 2 psi, ket psi, graph psi minus 1. So when I apply that amplification operator to this state, what I'm going to do, I'm going to rotate this vector in the direction towards this psi naught and move it by an equal amount forward. So, so I take this vector and I move it by some amount forward. The amount that I move forward is the same as this thing. So this angle now is also 2 cosine of inverse of n minus 1 n under root. So the probability of success, which is the probability of finding the solution, that I have reached my solution, how close am I to the solution, which is the probability of success in this case, is going to be dependent on this angle here. So I take the projection of this final blue vector onto my solution and take the modulus square of it. That will give me the probability of success. So let's do that. So how much is this angle? This angle is, so this is 90 degrees. So this much is pi by 2 minus this angle, which is cosine inverse of n minus 1 over n under root. And from this point onwards, I move another 2 times this angle, right? So this will be minus 2 times cosine inverse n minus 1 under n. This is where I land up after the first iteration. Alright? So now if I were to repeat the iteration, so if I were to do a second iteration, I will start off here, this will go here, right? This will go back here. This will then be reflected about this point again. So what, if you do this as a homework probably, if you do k iteration, this is where you will end up with. So after k iterations, this is the angle between your final state after the k iterations and your success and your direction of success. You take the cosine of this again. That will give me a projection onto my success axis and take the modulus square of this. This will give me the probability of success. Probability that I've reached my search. And you want to maximize this probability so you can find out how many k's do you really need. It turns out that the answer is proportional to square root n. So after square root n iterations, you get very close to your solution. Instead of doing n searches as you would do in a classical case, now you would have to do square root of n searches. So the improvement that this quantum algorithm offers over classical algorithms is not exponential, it's quadratic by the way. So the Grover's algorithm gives you quadratic query complexity as compared to the complexity in the classical algorithm, which is of the order of n. So the speed up is quadratic. And this is only, we're talking about the query complexity. How many iterations would you need? We're not talking about the complexity that is required to build the hardware or to build the circuits. So the last question that remains, by the way, this should be a homework problem. How do you get this k and how do you find out the optimal n that is required to give you to land very. So this is a cosine square function, by the way. So if you plot this cosine square function as a function of k perhaps, so this is a fixed angle, right? Some angle gamma. Depends upon the size of your search space, n. Only depends upon capital N, right? But what is variable here is k. So if you plot all of this with respect to k, all of this is a constant, so you'll get, I think, something proportional to sine, because this is a cosine of 90 minus something, you get something proportional to sine squared. So you'll get a curve like this. and you can find out the optimal K, optimal number of iterations that are required of the Grover iterator so that your probability of success is maximized. And it turns out to be proportional to square root n. Right? So I think this is a very valid homework. Now the last question I would like to ask you is this particular question. How do we implement this thing on a hardware piece, on a quantum computer? Now there are clever ways of thinking about this. One possibility is, let me first show you what the circuit looks like. So I'm going to show you an implementation of this operator, the amplification operator. So it's implementation, circuit implementation, because you want to build a quantum computer as well. You know somehow how you build a quantum oracle. It's a Toffoli gate or some version of the Toffoli gate, a doubly conditioned, doubly controlled NOT gate on some qubit, roughly. But how to build this thing? So, and I'm not looking at the ancillary, so the ancillary is something else. I'm not looking at the ancillary right now. So if I just had, say, 2 qubits, so I just focus on 2 qubits, this is how this circuit is built. 2 Hadamards, 2 NOT gates, Hadamard, controlled NOT gate, Hadamard, followed by 2 Hadamards. This is how you implement this. By the way, so there are different ways of coming up with the circuit. One possibility is the brute force approach, which is a nice approach. It might not look very sophisticated, but it's a nice approach if you're doing things for the first time. The brute force approach says that really it literally means you're applying brute force. So look at this vector here. This is an operator, it's an outer product. So find a matrix for this. So can you immediately tell me what the matrix for this is going to look like? This is an equal superposition of all states. So what does this outer product look like? An equal superposition of all states. It's a 4 by 4 matrix. Just on the diagonal. All of them will be ones, right? And this is 2 times that, right? So it's all ones. So there's halves everywhere, because this state really, this ket psi is 1/2. So when you do a dot, when you do this outer product, so this is this thing, and then I multiply this with 2. Correct? So I think I will get halves everywhere. Then from this I subtract the identity. So I will eventually get a matrix that has zeros on the diagonal and is non-zero everywhere else. Right? So now I would like to build a combination of gates that has that unitary form. And one way to do this is just by brute force assembling these gates. By the way, if you were to look at this carefully, if you just look at this part, just this part is really ket 0 0, brass 0 0 minus identity. can work it out on Qiskit or Mathematica. And then on the two sides you have these unitary operators, these Hadamard unitary operators. So these unitary operators, actually these unitary operators are here. These unitary operators, the Hadamard, are here because time flows like this on the diagram and time flows like this when we write down the propagators or the unitary operators. Okay, so what you could do is really you can expand this. Let me write this as a big FH, big FH, a 4-qubit Hadamard, a full Hadamard matrix, FH. So FH minus this acts on this acts on this. This is identity. The Hadamard is itself inverse. So this gives you identity. And if you work this out, this gives you, so now you are inputting this, so 0, 0, and you apply full Hadamard onto this, this gives us the full operator. Right, so this will turn out to be 2. So the 2's come out somewhere. So this is FH 0, 0, FH. Let's do this properly. FH 0, 0, FH minus FH. So this is exactly what I've written over here. So this turns out to be 2 psi, ket psi, graph psi minus 1. So you can work this out on your own. The Hadamard is itself inverse, so you put 2 Hadamards back to back, you get the identity matrix. And so what's really happening here is after this oracle, you pass this through an amplified circuit. That amplified circuit has a sequence of Hadamards followed by a reflection about this state 0, 0, followed by another Hadamard. This is how you would implement overall the Grover algorithm. Any questions about this? So overall the scheme is as follows. And this is how many quantum algorithms work. You initialize, you create a superposition, somehow you would like to add an ancillary qubit, that ancillary qubit sucks in some phase, and then you define a function that you would like to implement. You have to cast it into a unitary operation because that's what quantum mechanics is all about. It's a unitary operation. So that function, that logical function, which is given over here, I think, somewhere here. Sorry, I don't know where it is now, but somewhere. That function, this one, this function has to be cast in the form of an oracle. So you already know the function and you already know what you're looking for. So you design your circuit keeping in view that you know what you're looking for, and then use that primitive or oracle or toolbox later and test it upon unknown states and come up with a mechanism to sample your solutions from an undesired heap. That's what an oracle does. So you apply a unitary transformation. If you're doing searching, you have to amplify your solution. And there's a mechanism to do that. And that is through the amplification operator. The amplification operator is simply doing reflections on this circle. It's nudging your state closer and closer to your desired subspace. By the way, this could be one state or it could be a combination of states. That's why I use the word subspace here. So it's nudging your state as it is propagating through the algorithm closer and closer towards your desired subspace. Finally, it lands somewhere, and there is some angle between your final state and your desired state, and you would like to make that projection as large as possible, because if this were an angle, the modulus squared of the cosine of this angle is going to give you a probability of success. That's how this algorithm is really working. So the next lecture, so I think now is the time to prepare for the second homework. I would like to announce something about the projects. I think what you should really do is look at different kinds of algorithms, and for each algorithm you might like to come up with a theoretical description, a mathematical description, a pseudocode, and implement that algorithm on two platforms. One, a quantum simulator, two, a real quantum computer. And the development platform of my choice or Abdullah's choice is Qiskit, but you can also use Microsoft, U#, anything, or if you want to do it in a simulation form, you could also do it on Mathematica or Python as well. So this is, start thinking about your projects now. In the next lecture, what we're going to do is we're going to look at something more complicated. By the way, all of this is slightly terse. It's a lot of mathematics, lots of juggling around, so it requires a lot of my attention, a lot of my focus as well. The next lecture is going to be slightly more complicated. It's about the quantum Fourier transform. So that quantum Fourier transform is again a subroutine in other algorithms, notably the Shor's factoring algorithm. That's what gave quantum computing and quantum information processing the prominence that it really deserved in the first place, that you could break e-commerce codes and so on. So that's about finding the prime factors of a large number. So we have to go towards Shor's factoring algorithm, we have to go towards eigenvalue problem solving, we have to go towards quantum simulation, but for that we need to know how do we estimate phases. That's the quantum phase estimation subroutine, but for that we need to know the quantum Fourier transform. So how many of you are familiar with Fourier transforms? Okay, almost all of you. So we'll look at the quantum version of this in the next class. Thank you.